So first is molecular geometry. You guys can do this at the end or now, it's up to you. So first is molecular geometry. Molecular geometry depends on the number of groups attached to the central atom. So that means other atoms and lone pairs. Here, there's two lone pairs, and two atoms attached hydrogens. So oxygen is therefore attached to 4 groups, 2 lone pairs, 2 hydrogens. So the electron geometry of this would be a tetrahedral. However, its molecular geometry would be bent with a bond angle of 109.5. If you guys have questions, it might be faster if you guys unmute yourself and ask me instead of typing. It's just in case I don't get the chance to read it. So here is a table. You guys should all have this inside your textbook. It may vary, but this was taken from the textbook as well. So you guys can either take a screenshot of this or you guys can refer back to this in a bit. So this is the first part. There's a ladder part to this table. And I would say use this to refer to this or the table that you happen to have with you for the following practice problems. Okay, next one. So this is the next part. So this is electron group, in black, group, bonding. This is electron group, bonding group, lone pairs, electron geometry, molecular. I'm just going to write like that. Approximate angles. And the general shape examples right here and how they might look when you put them, you build them. So the practice problems, I'm just going to give you guys each 5 minutes to do it. Let me know if you guys need more time. So I'll give you guys 5 minutes from 7, or just finish by 7:15. Or if you guys finish earlier or need more time, just let me know in the chat. So it's phosphorus trichloride. I want you guys to determine, so tell me the geometry. Molecular one. Oh, electron geometry. Molecular geometry. Bond angle. And compound. Polar or non-polar? And I want you guys to show this using your partial positive, partial negative charges. So 7:15 or 7:16. How about we go over this one then?
Yeah.
So I'm going to share my, can you guys see? Can you guys see? Okay. So the first thing I did was to count it. Did you guys all come up with this?
Yes, 26 kilometers.
With the structure?
Yes.
Yes.
Okay. So I'm going to unveil the results of what I did now. Sorry. So first, if we refer to the previous table, so we have 3 bonds plus lone pair, right?
Yes.
If you go to the table, where the only one with 3 bonds and a lone pair is this row right here.
Pyramidal.
Yeah, right here.
Yeah.
So it's tetrahedral in electron geometry. It's trigonal planar. I mean trigonal pyramidal for the molecular, and the angles are less than 109.5. So listed those. Now with partial positive and partial negative, remember you're looking at electronegativity. So if you look in your textbook or maybe in your PowerPoints or your professor slides, they might go over the electronegativity regarding using the periodic table. So in relation, chlorine is more electronegative than phosphorus. I don't know how you guys see me, but basically, so chlorine is here and phosphorus is here. The further to the left towards fluorine it is, the more electronegative the atom is. So that's why chlorine in relation to phosphorus is more partially negative. So adding to that with the partial negative of the lone pair, you have a polar compound. If we didn't have the lone pair, you would actually have a nonpolar compound. Because all of the forces, what would happen is the net dipole moment would cancel out. In this case, we have lone pairs, so they don't, which means that we have a polar compound. Did I lose anyone at any point?
Yeah, on the, maybe just like a clarification on the net dipole moment a little bit further.
Yeah, so what I mean by that is, so if I took this out, right? If you're pulling something in all directions, the net dipole moment, I'm just going to write net dipole moment would be a straight line. Well, we'll actually be pointing towards you. It's almost, if you, let me think of it a different way. Okay, so if you're pulling something like this, right? If you're pulling them that in opposite directions, you're kind of going in almost no direction, and it's going in a path towards you versus in one direction. So if there was no lone pair, you'd have a net dipole of 0 because they all cancel each other out because it's evenly pooled.
Okay. Because they all have the same amount, like surrounded the chlorine.
So with the 3, they would be equal distant.
Okay.
But because we have the lone pair, and because then that makes our angles different now, so it's less than 109 degrees, you'll have a net dipole of negative going in one direction, in another direction. So it'll actually pull you down towards the electron, the lone pair. So that's what makes it polar.
Okay, got it.
Okay, so the next one, give you guys 5 minutes again to do it. ICl4 minus. So just a heads up, the compound, you don't have to draw that. What you'll do is a minus on the outside. And don't forget to add your extra electron in when you're adding up how many you need to have total. So again, I want the same information, electron geometry, molecular geometry, and so on and so forth. Okay, so I didn't fill in the electron geometry or anything. I wanted to get your responses for that this time. So did you guys get this shape, the structure, as well as the number of electrons that should be accounted for?
Yeah, I got the shape. I just wasn't sure after I filled in everything what to do with the 2 extra lone pairs.
Yeah, so you can put them on to the structure around the central atom like this, or you could do them on opposite sides. It's just up to the person, up to you, personal preference there. What did you guys get for electron geometry?
Octahedral?
Yeah. What did you guys get for molecular?
Square planar, I think.
Yeah, I got square planar as well. Anyone else? Did you guys get something different? No? Bond
Yes.
angle? Oh, yeah. Did you get something different?
Yeah, I get the geometry for the
Mm-hmm.
tetrahedral.
So you got octahedral for the
Uh, Tetrahedral.
tetrahedral? Okay, so
Uh-huh.
let's look at that real quick. So what you'll see is this right here. Right here. So it wouldn't be octahedral and square. You got square pyramidal, right?
No, for the tetrahedral.
Tetrahedral?
Uh-huh. Which is I just put the bond, I didn't put the pair on the
Yeah, okay. So that's where you probably got confused, because so there are two lone pairs on iodine. So when you put it on, it'll follow this structure right here where you'll have octahedral and square planar with a 90-degree angle. So again, with that, I would always recommend counting your electrons, because if you miscount it, then that would change your geometry, your molecular and electron geometry. So it has a bond angle of 90 degrees. So when you guys drew your partial negatives, I'll just put positive once here through. Did you guys put polar or non-polar?
I put polar.
Yeah. Did anyone put differently? Did anyone put non-polar or no? Everyone put polar.
Can you explain why it's polar?
So it would be polar due to the lone pairs again in this case. So if it was typically tetrahedral, everything would be equidistant again. And everything is 90 degrees apart, but you also have now two more going out like in this direction. So imagine a cross and arrows all going out in the opposite directions. But if you have two more factors here, it will pull it upwards. Imagine it that way with the way I have my lone pairs. So it will pull it like this. This is what we had.
Oh no, I get it now. I completely forgot about the lone pairs, and I was focusing on the fact that I had the 90 degrees and
yeah,
it was even, quote unquote. But that totally makes sense.
Yeah, don't worry about it. We'll catch these, because sometimes that's the tricky part when you're labeling it or filling in a box for your exam. So it's better to, at least we figured it out now, and you can look out for it later. Yeah, so the lone pairs, just imagine it like that with if I draw it on an axis. You can see it would, in general, would pull it in an upwards direction. Yeah, so that's why it's polar. So this one, 735 for SCO4. Okay, so I'm going to just share my screen and show you guys what I have so far. Did you guys get the same number of electrons in the structure?
Yes.
Yes.
Yeah.
Yes. Okay. So what did you guys get for your electron geometry?
Trigonal bipyramidal.
Trigonal bipyramidal? Yes.
And then for molecular seesaw.
Yes. So did the bond angle confuse you guys? Did you guys get the same bond angle?
I didn't even do.
What
a
did you
bond
put?
angle.
Oh, okay. Yeah, so the bond angle for this one is more tricky to see, because we're usually drawing this in really pretty much 2-dimension, but the bond angle that they give you is for the 3-dimensional figure. So if you'll learn this, you probably have not done this too much in Gen Chem, Intro, or even in 2A, really. So you can draw your structure like this. I won't fill in the electrons, but there's this lone pair here too, right? So the distance between this to this is about 118 degrees. So this is the less than 120 degrees for that angle part. And this, they say, label it as equatorial because it's pointing out from the page. So this is very much seeing this in the 3D. This is just to explain why they have 120. And the 90 degrees would just be between like these two, less than 90 degrees, or these two right here. This is, you probably won't have to do this, but this is just for explaining why, the reasoning behind why they have those two angles. So for polar or non-polar, what did you guys get?
I got polar.
Yeah, it should
Polar?
be polar. I think.
Yeah. So if we draw the partial negatives, partial positive here, and that lone pair again comes in and pulls it to a certain direction, and that gives it that the polar and non-polar. Okay, and this was the last practice problem for this part. I'll give you guys challenge ones at the end that you guys can do on your own. So the next part we're going to go over is molecular orbital theory. Okay, another student's joining. So molecular orbital theory. So what we'll do is I'm just going to briefly go over it about hybridization, and hopefully your class has gone over it already or will be doing so soon. So it'll give you guys some practice. So when there are two electron groups, it would be considered linear. So this is an sp group. This is an sp2 group, and they're typically associated with an electron geometry of a trigonal planar, where you have 3 electron groups connections. So there's 1, there's 3 bonds, and then there's 4 bonds, tetrahedral, which is an sp3. So just recall that these are associated also with the number of electron groups. So even if it's connected to it, even if it has like a double bond and it's connected to 2 others, it would still be connected to 3 groups. And you wouldn't count the double bond as a 4th bond. Okay. So practice problems. Give you guys 5 minutes to do this. So determine the hybridization of the following molecule. I'll help you guys with the first one. This oxygen earlier that we were talking about, it's supposed to be sp3 because when you draw it and you put in the lone pairs, those create orbitals themselves as well. So when you're counting these lone pairs in, that's 1, 2, 3, and 4. So it would be sp3.
So then we have to, when we draw, we have to draw the pool.
Yeah, so this isn't the case with lone pairs. If it's a double bond, that's a different scenario. So double bonds, you treat them as, this would just be 1. This wouldn't be considered 2 bonds because you're connecting to different atoms. So for this oxygen right here, what did you guys put?
So it has 2 lone pairs. Yeah, we have to write down.
So this would be how many connections?
4.
It'd be 3.
2, 3. Yes, 3. So it
it'd be
is sp2. sp2.
How about this carbon?
The carbon is sp2,
So
sp3 because it's for
sp3.
tetrahedral.
Yeah.
Yes.
How about this carbon right here?
Which one? Because you didn't.
This one.
That one is 1,
Yeah.
2, 3. 3. So it is sp2.
And then this one,
sp2.
sp2. If anyone got different answers, chime in. The next one, the one to the right, the
sp2.
first closest one. This one,
Yeah, sp2.
sp2. And the last one,
The last is sp3.
everyone gets the same answer?
Yeah, except the oxygen on the second one that you solved.
Yeah, so the second one, we treat it almost the same as earlier. So if I draw another orbital like this, because it has 2 lone pairs, and it only has another connection to a carbon, even though it's a double bond, you're considering it connected to a different atom. So that's why you treat this as 1 bond, and I wrote 3 right here. So it's connected to 3, so that means it's an sp2.
Okay, so then for some of them, you'll have to like kind of, is that like making an additional like Lewis structure for it, or for some of them?
Yeah, so it's only when you have the lone pairs, you can draw them in like this, or if it's just drawn like this, it's up to how you can visualize it. If you see the lone pairs, you can count them as one group like that. You can just circle it.
Okay, so then
Yeah.
for some of them, you might need to do like additional like visualization or just counting the valence for the pairs. Okay.
Yeah, so it's not only with oxygen, sometimes you have it with nitrogen as well. So you just want to double check with if they have lone pairs.
Okay.
Yeah.
Thanks.
So I don't know if we'll finish the remaining problems. I'll give you guys the option. Do you guys want to do this hybridization, or I can add it to your challenge problems, and then we can go into the molecular orbital diagram?
Sure.
Yeah? Okay. So this will be challenge. So this is the molecular orbital energy diagram. We'll do the first one together just because it's easier to see it. So I'm going to draw it. This will be your reference. Typically you can use this so they'll put down, we put down here, you can use this diagram specifically for B2, C2, N2. O2, F2, and Ne2, you would use this one. So let's look at the first one, and it's lithium. So let's write out the electron configuration of lithium. And lithium is 2s1. So 1s2, 2s1. If it's Li2, you want to draw them like this. So there's Li here, Li here. So you'll have a 2s, and you'll have a 1s. I know it's a little tedious to draw them like this. It's up to what your professor prefers. You might not have to draw this whole orbital, and you can just draw them in stacks of boxes. The reason why I'm drawing them like this is because in the middle you have your Li2 bond. And in this case, so you have your 1s and your 1s on each side, but with your s, you also have an antibond. Your antibond, you'll have a sigma. So this is sigma star 1s, and this is sigma. This is just sigma 1s. So the same applies for the 2s. Oops. So this is sigma star 2s. Sorry, it's drawn kind of big. What happened? Okay. 2s. This is sigma 2s. So earlier we counted, so this is a total of 3 electrons for each side, right? So if you're filling it in, so you'll have your 1s, you'll fill it, 1, 2, and then 3. So do it, you fill it out like you would fill out your Hund's rule. So you'll fill out each first, so 1s, 2s. I mean, 1s is filled completely, and then it goes into 2s. And the same applies, same rules apply for your sigmas, 1s. And here, what will happen that is the unique case is that for the 2s orbital, you're only filling 1 from each side. And you don't go into your sigma. And that's because if you took this one only and this one, they add up for a total of 2 in your sigma bond for your 2s orbital. There isn't any in your sigma star. Any questions?
I haven't learned this, but would you be able to quickly explain what like sigma is or what that means?
So sigma, this is more into, so you have, let me go into the previous table right here. So here you'll see that we have a pi and a sigma bond. They're just a type of bond that you can see like a visual of this. It's kind of similar to this, where it would be applied to, again, this is very much kind of like a theoretical side to the molecular orbital energy. And this diagram is just a way to fill it out with your electrons versus drawing it. So it's, I don't know, it's a little hard to describe, but typically, so here, I think the best thing I can say is that typically you won't stray outside of these tables, these examples right here. So these are your basically your template for these possible elements that your professor could give you. The one that we just did for lithium, that one is an easier one, just because you only go into the 1s and 2s. So we don't even have to do 2p for this. Here, there's another example
So
that
I do a quick question without making you explain it to everyone else.
Yeah.
But if would the bond order then be 1 for that problem?
Okay, so bond order. So
I mean, I don't want to make you explain that to everyone. I'm just trying to get it.
Yeah, it would be. So it'd be 2
Okay.
minus 1. Yeah.
Okay.
Mhm.
Thank you.
So this would be the third problem. How about I'll just show it to you guys here, so the video can catch it. You guys can screenshot it. It's up to you. Here are challenge problems. So I made a key for it already, and I'll send it out to the other tutors. It's up to you guys if you guys want to complete it. I'd encourage you guys to. It's extra practice. So these are problems that you guys can do and check with by scheduling another tutoring appointment with another tutor or even myself. So this is the first one. The second challenge problem. The third, again, with the labeling. This time I numbered it. The fourth, fifth, and sixth. This is the last problem.